Good morning, everybody. First of all, thank you very much for inviting me to give a lecture here. So lecturing for auditorium of Moscow State University is very special for me because this is my alma mater. So I really enjoyed this. I really enjoy being back and present some results which I achieved. And today I will talk about I will stop video now and then switch it on when I'm ready for questions, but you can interrupt me at any time. So today my topic is the basics, approaches, and applicability of satellite remote sensing. And today I want to start my presentation from this video. When I saw it first time, it was really breathtaking for me because here I see partly results of my work and the work of my colleagues. So please take a look.
How do you see the atmosphere? The answer is blowing in the wind. Particles known as aerosols are carried by the air around the globe. This visualization uses data from NASA satellites combined with our knowledge of physics and meteorology to track three aerosols: dust, smoke, and sea salt. Sea salt, shown here in blue, is picked up by winds passing over the ocean. As tropical storms and hurricanes form, the salt particles are concentrated into the spiraling shape we all recognize. With their movements, we can follow the formation of Hurricane Irma and see the dust from the Sahara, shown in tan, get washed out of the storm center by the rain. Advances in computing speed allow scientists to include more details of these physical processes in their simulations of how the aerosols interact with the storm systems.
So maybe I stop here. You can watch this video later. I provided here the link. But as you probably understood, this video is the result of combination of remote sensing data, model data, and ground-based data. And today we will talk about how to get the remote sensing data and what actually the remote sensing is. So remote sensing is the science which obtains the properties of the air, of the area or of the object, which is located at quite some distance, quite big distance from the instruments. And this is the difference from the in situ observations. Remote sensing is the acquisition of information without making physical contact with the objects. This is the technique which allows to capture, to visualize and analyze objects, and it uses a sensor to capture a signal or an image. Remote sensing instruments are installed on different platforms. And I will talk later about this in more detail. But here I want to start with the basics of remote sensing, which deals with the data collected by electromagnetic energy. The orbital platforms collect and transmit data from different parts of the electromagnetic spectrum. What is electromagnetic spectrum? You probably know this basics from your course, from physics course from school or high school. But just short reminder. Electromagnetic spectrum is the full range of frequencies of electromagnetic radiation and their respective wavelengths at photon energy. And wavelength is a period, is the special period of periodic wave. And in remote sensing, the typical application include the visible light, which is in the range of 380 to 780 nanometers, infrared and microwave ranges. If you look at a picture here in the middle, so what happens with the sunlight, which is emitted from the sun? So it goes down in the direction to the surface, and on its way, it meets some obstacles. Those obstacles are clouds, gases, or aerosols. Some of them allow part of the electromagnetic energy transfer further to the surface, but some of the energy is reflected or scattered from those objects back to the Earth. What if there is no obstacles? Then the solar energy reaches the surface, and then it's also absorbed and scattered by the Earth, and then it's transmitted back to space, back to the instrument. So the satellite, it gets the signal which is emitted by the sun, but it is absorbed or scattered or transformed back to the Earth and back to the atmosphere. It is estimated that only 67% of sunlight directly hits the Earth. So the rest, 33% is reflected back to the atmosphere. And remote sensing is based on the principle that each part of the spectrum has different characteristics and give different information about the Earth's surface. So if we look at this picture, you can see that the upper curve, it shows us the solar energy curve at the top of the atmosphere. This is amount of the energy which is emitted by the sun in different wavelengths. So on the way to the surface, part of energy is transmitted back, and this colored line, this red line or red area, is the energy which is transmitted to the Earth. And the yellow color shows the energy absorbed by gases and air, including water vapor, carbon, ozone. And as I told, the different species, different gases, they absorb solar light at different wavelengths. So this allows us to retrieve the amount of gases based on the knowledge at which wavelength the gases absorb solar light. On the previous figure, you saw the signature of the absorption lines, and here you can see the spectral signature of different subjects on the surface. So as I told, the absorbance, reflectance, transmittance coefficient, they are highly dependent on the wavelength. And spectral signature is the reflective behavior of an object along the electromagnetic spectrum, and specific combination of those coefficients can allow us uniquely define the characteristics of the objects or the surface. Very shortly about radiative transfer. It's the physical phenomenon of energy transfer in the form of the electromagnetic radiation, and here is the mathematical equation which describes this process. It's quite complicated equation, and the analytic solution to this equation exists for simple cases only. And to solve more complicated cases, we need numerical methods, and we also have to assume to make quite many assumptions to solve. Now we move back to satellites and satellite instruments. And first, I want to introduce you the types of satellite orbits. So when rockets is launched, it's put into the orbit, and the list of the most popular orbit is here on this slide. So namely, there are geostationary orbits, low Earth orbits, medium polar orbits, some transfer orbits, and Lagrangian points. Characteristics of geostationary orbit and low Earth orbit are here. The satellite in geo orbit, it circulates Earth about the equator from the west to east, following Earth rotation. So it travels at exactly the same rate as the Earth. and that makes the satellite geostationary. So we can achieve the information from this satellite over exactly the same area, always over exactly the same area. The low Earth orbit is normally at the altitude less than 1,000 kilometers, but it can be as low as 160 also. They do not all, LEO satellites do not always have the following path around the Earth, so they're not at the same place at the same time. And those orbits are most commonly used for satellite imaging. I will talk about imaging later. Medium Earth orbit, it's the wide range of orbits, and it's often and very commonly used by navigation satellites. But since we are here talking mostly about the environmental data, so we are not very much using data from those orbits. Polar orbit and sun-synchronized orbits, it's the most popular orbits for the remote, for the environmental sciences. They usually travel past Earth from north to south rather than from west to east. And those satellites are passing roughly over the Earth poles. They are a type of low orbit, and operate, their satellites operate at altitudes between 200 and 1,000 kilometers. Sun-synchronized orbit is the particular type of the polar orbit, and that means that the satellites are located at the same position at the same time of the day. So they visit the same spot at the same local time. And this allows for the number of application. So we can compare the changes over the same area over the same time. Instruments which are on the satellite platform, there can be of two different types, passive and active. So the remote sensing, which measures energy that is naturally available, it's called passive remote sensing, or those sensors can only be used to detect energy when there is the natural natural energy is available, or in other words, when the sun is illuminating the Earth. And energy that is naturally emitted can be detected day or night, as long as there is the amount of energy is large enough to be detected. Active sensors, on the other hand, they provide their own source for illumination. The sensor emits radiation which directed toward the target. An advantage of those active sensors is that the measurements can be taken at any time regardless the time of the day or season. And those active sensors, they can be used to examine wavelengths that are not sufficiently provided by the sun. So as an example are microwaves. Remote sensing instruments, they can be divided into two big instruments, imaging sensors and non-imaging sensors. Imaging sensors, they measure radiation at different points of the target, and then this information is used is processed in order to obtain the image. And those instruments, those sensors, they are used when we are interested in the special information around the target, and when we need the information in the form of a map. Non-imaging sensors, they measure radiation received from all points. Then this information is integrated and registered as a single response value. And then the images can be done from those data. Imaging sensors, in turn, they are divided into optical, thermal, and radar imaging sensors. Non-imaging sensors, the example of non-imaging sensors are spectroradiometers, radiometers, and altimeters, among many others. So shortly about the imaging sensors, optical sensors, they are operating in the visible and reflective infrared ranges. And the resulting images can be used to recognize objects, to identify material, and also for many other purposes. So radar images, they operate in the electromagnetic range of 1 micron to 1 meter. The sensor transmits the light to the ground, and those sensors, the advantage of those sensors is that they can operate in the cloud or foggy weather. Thermal sensor operates in the electromagnetic spectrum roughly between 9 and 14 microns. And then commonly used thermal sensors include imaging radiometers, spectroradiometers, and infrared imaging cameras. Non-imaging sensors are listed here in the table. On the left column is the sensor name. Then I show the operational waveband, and then a definition or where the radiometer are used, for what they are used. Very quickly, the most popular and most commonly used, as I already, radiometer, altimeter, and spectrometer. LiDAR are also very popular because they often give an additional information to the information update from the other instruments, and application of those sensors is quite wide. Here is the list of the types of the satellite products. So what basically we get from satellites are the data which are ranged into 5 different levels. Level 1 data obtained is the satellite direct radiation. In level 2 product, calibration and geolocation are already applied to the measured data. And in the level 2 data, the actual product is retrieved. So the information obtained from satellite, it's converted to the physical unit. Level 3 is the processed data. As example, are gridded maps. And level 4 product is the interpolated product, which is created by users. Few words about the global climate observing system. The GCOS was established in 1992 to ensure that the observation information that we get from satellites, they're of needed accuracy, and the information is available to all potential users. And GCOS identified the essential climate variables based on the following criteria. So those climate variables, they should be relevant, feasible, and cost efficient. That means that those ECV, which we obtain from also from satellites, they have to satisfy all those criteria, and they are critical for obtaining the climate information. Next is about different initiatives which are developed to promote or to develop the system of measurement system, which starts from measurement, then data processing, and then the last, and which is very important, is the access of the data to the users. The ESA-CCI initiatives, it's the program where satellite data records are key components, are considered as the key components in the climate system. And this program has been started maybe since 2 decades. And our group and FMI, it is involved in different projects, namely like aerosols, greenhouse gases, ozone, and others. And here I showed some examples of the ESA CCI product developed at FMI. Not general ESA product. So land cover, it's not FMI product, sorry, it's a UK product. Then land cover, soil moisture, snow extent is FMI product, aerosols is FMI. And biomass is also CCI product. Introducing here the FMI product, aerosol FMI product, I would like to mention that there are quite many limitations in the remote sensing, and those limitations they are based on the product. For instance, for aerosol, the main limitation is that remote sensing instruments, which we use to retrieve aerosols, they do not stay above cloud. So cloudiness is the main obstacle. So with remote sensing with satellites, we can never get the global coverage of aerosols, for instance. This is different from modeling, which can estimate aerosols both in cloud-free and cloud conditions. Also, bright surface is not easy to retrieve for aerosols because the signal transmitted back to the atmosphere from the bright surface is much stronger than the signal from aerosols. Also, solar zenith angle is a problem in the retrieval. So for high solar zenith angle, radiative transfer mechanism or codes, they're not working as they should. We also make quite many assumptions regarding aerosols. We assume the vertical profile because what satellites can see, what radiometer can see is the total column, but not the vertical distribution. We also assume aerosol components. But even with those assumptions and even with those limitations, we developed the product which is quite widely used by modelers, and which is used, for instance, for evaluation of radiative forcing or evaluation of aerosol product from models. Now, next step is to the introduction of the different satellite missions. So I start from ESA, and here is the list of the currently flying and planned instruments, which can roughly be divided into three different sections. So the science and meteorology are on the sides, and the Copernicus instruments, they can be also used for both science and meteorology. So quite many instruments, and what I want to mention here specifically is that it's a quite long way to plan a satellite before it's launched. Usually it takes 10 to 15 years to discuss and to build the satellite. So we have to think much further in advance to imagine the technique and all applicabilities like data storages, everything which might be accessible in the 10 to 15 years. Otherwise, if we use only current knowledge and no plans, so then in 15 years we will launch the instrument which is already old regarding the technique. Copernicus program is also ESA and EUMETSAT program. It's coordinated by European Commission, and it includes different subjects like climate change, marine monitoring, atmospheric monitoring, and others. And Copernicus, it's the system of satellite and airborne and ground station data. And the aim of the combination of this is to supply the global monitoring data and operational services. Copernicus Sentinels is the current main European satellites flying and still planned. Sentinel-1 provides all-weather and day and night radar images. Sentinel-2 is used for land services. Sentinel-3 is the optical radar and altimetry instrument. What is specifically has to be mentioned here is Sentinel-5P. It's the precursor for Sentinel-5, but this is the instrument which flying already, and it provides the information about greenhouse gases in very fine resolution. So it's now very, very popular, and the data are used in many applications from this set. Here is the NASA satellite and missions which are planned until the 20th. So it's not the up-to-date picture, but this is what I could. Also, the NASA agency or European agency, they are not working separately. They work in combination with each other, and many satellite missions are the missions which are built by the international partners. Here is an example of Japanese satellites flying already, and here are Chinese satellites. And the Chinese missions, they're in general different from the others. And the difference is that most of those satellites, they're small satellites, and they can measure at 1 or 2 wavelengths only. But it's much cheaper to build this satellite. And the advantage of those satellites is the coverage. So there are many of those flying, and information is and the data update from those satellites is of very fine resolution, though everybody knows that it's not easy to get access to Chinese data, but we know that those data exist. Next is about data access, which is important, very important. And the policy in Europe has changed maybe 5 years, around 5 or 10 years. The discussion started maybe 10 years ago, that all the data produced by scientists, they should be of open data access. So what is needed is registrations, but registration, but the scientists, they do not pay for the data anymore. This is the list of the data providers based on the agencies. You can find data here, but what I most recommend to the students is to start from looking data at those 3 servers. They are good in a way that you do not have to download the data in the original format, but you can extract area, you can extract period, you can even plot some data. And in a world view, for instance, NASA, it allows plotting different variables on one map variable. So it's very, very nice tool. So please start from those when you will start looking at the data. Application of remote sensing is very wide, and maybe I will not list all those, but in the next slides I will show the application which are developed at Finnish Meteorological Institute. Not this slide, but here are just the examples of applications. So with satellite, we can follow the volcanic eruption, or we can see the change of the snow cover. or we can look at the different rock types using the pulse color image, which is based on a combination of several bands. So agriculture, suspended particulate matter in the coastal waters, Mediterranean wildfires. So most of those products, they're just images, but we also retrieve aerosols and different gases and look at this snow cover with the satellites. This is example of the FMI and FMI products for EUMETSAT satellite application. And what is retrieved is the traced gases, ozone, NO2, SO2, and aerosol and radiative products. We also develop satellite UV products at FMI in the frame of SAF UV product and from the Tropomi instrument and in the ESA 5 product. So those are the UV data retrieved from satellites. And a bit more about UV observations. We don't use only satellites, but we also have ground stations where we can evaluate our products. So we get data from satellites, get satellite product, and then we compare that satellite product with the ground-based data to see how good or how bad or where are the problems in our satellite retrieval. We also use satellites in air quality, looking at, for instance, on the left, it's the OMI NO2 observation. We detect the concentration of cases in the area of Helsinki, for instance. And this information is immediately forwarded to the users. So they have 24 hours access to the information about the air quality. This is another example of air quality monitoring. Other application is that we develop satellite-based proxies for new particle formation, for aerosol formation. We monitor shipping emissions looking at the NO2 concentration. And we also develop the operational sample near real-time service where data can be accessed in almost near real time. We look also at the cryosphere, which is very let's say burning topic in the northern latitudes, and we deliver the daily near real-time product for the northern hemisphere of the snow content, water equivalent, and lake ice extent product. We are also monitoring sea ice using satellites. We also provide data for climate research within the ESA CCI, which I mentioned before, and for Copernicus service. Here on the left is on the right is ozone trends and ozone concentration and ozone trends. We also look at the different variables to detect fire activity and air quality. Here is the combination of the fire radiative power and then anomalies of different species. For instance, AFD anomaly, absorbing aerosol index, CO2 anomaly. Look at the combination of those to detect the contribution of fires, as an example. Since the satellite data are already available for a few decades, let's say 2 decades, so we can see back and we can look at the what was the situation many years ago, and we can calculate trends. This is example of aerosol product, which we developed at FMI, which is the merged satellite product. And the advantage of this product is that it uses it combines different satellite products. Thus it have the best temporal coverage back to 95, and then it has best resolution. So this product is freely accessible at FMI, and it has been already used by modelers for model verification, for example. And the data are stored at the NCDC FMI server. And what is NCDC? Is this the FMI Arctic Space Center? There we obtain satellite data in near real time. Then we store them for users, and we also store a product and monitor the atmosphere 24 hours a day. About advantage and disadvantage of the remote sensing. I start from the disadvantage. So it's quite expensive method, and it needs quite expensive instruments, and some limitations like for others, the big antennas need for big antennas. So it limits the usage of radars of the remote sensing in this way. So the other thing is that once we send instrument to the orbit, it's not easy to calibrate it if it's in operational for a few years. So good if there calibration system, if installed, if possible. If not, then we have to somehow calibrate the data with the ground system, which is not always easy. Also, the other problem is that we have to solve inverse problem. As I told before, we know signature, we know the spectral signature of subjects, and then we track back, and then we have to solve who left that signature. But with this, it's not so pessimistic. There are quite many advantages of the remote sensing. First of all, it covers the large area, and depending on the orbit, it allows the repetitive coverage. Also, remote sensing allows for easy collection of data over a variety of scales and resolution. And the data can be used in various applications and for different purposes. Also, this information can be obtained quite fast, quite processed and obtained quite fast. Here I listed the great challenges or future plans. So the scientists are thinking about the increasing spatial and temporal coverage and resolution, also increasing informational content. For that, the state-of-art data processing approach has to be developed for the next generation of satellite. And the very important thing is that every next satellite, it has been developed in consistency with existing satellites that allow us achieving the continuity of the data for estimation, for trend estimations. And I want to end with showing again the same picture, the same from the movie I started with. And the big challenge is that, which I already said, it's the creation of new applications should be based on the integration of satellite, ground-based, and model data. And here are some additional links. Thank you. That was all what I wanted to show.